Hello, in this video we want to find the distribution of the distance of one point from the origin, or the distribution of the Euclidean norm. In this example, we consider that we have two random variables, x and y, and the output function is square root of x2 plus y2, which is r, and here is that if you have a random point, this is x, this is y, and this is r, so the distance of the point from the origin, and we want to find the distribution of this point. In this case, we see that it is easier to work with. Let's say if I define dr means the set of all points pair of x and y, such that the value for these, which means that x2 plus y2 is smaller than or equal r. Basically, this is going to be a circle centered at the origin. So all the points. So if this radius is r, so dr is all the points inside the circle. So the CDF of r will be integral inside this circle of radius r. So we need to be able to put the boundaries of this integral. So I have to put either outer part as x or y, and then so the way it is written, dx is the inner integral, and then dy is the outer one. So I have fx y of x and y that I have to integrate, and then I have to integrate with respect to y, okay, and then x. Okay, so if I'm inside this integral, this circle, inside this circle, so let me clean it up. Inside this circle, the maximum values that y can take on is, let's say if you're dancing inside this circle, the lowest part on the y-axis you can go is from minus r to the maximum value is plus r. Now, if you are on a specific value of y, the minimum value of x starts from this side of the circle to the other side. So for a specific value, and on this circle, I have x2 plus y2 is equal to r2. So if the value of y is fixed, so then I could say that x2 is equal to r2 minus y2, and therefore x, the solution on the circle will be plus minus a square root of r2 minus y2. So the boundary of the integral will be, I clean up here, will become minus the square root of r2 minus y2 to plus a square root of r2 minus y2. Okay, so this is one way to do that. Some people, they may want to say, oh, because I have a circle, so I could convert everything into a polar coordinate. So this is, in general, this is the expression, and you can use this one. So if you have circular symmetry, if this function is only a function of the radius, okay, and then you could simplify the integral of the previous page into this one, because if you remember, this was integral over the inside the circle of fxy of x and y, and then dx dy, and this guy is a function of g of r. So if you convert Cartesian coordinate to polar coordinate, you could quickly get this result. So this is for any pair of circularly symmetrical random variables, the CDF of the distance can be quickly calculated from here. Now, if you calculate the derivative of this one with respect to dr with the radius, you see that only the upper part of this integral, only this one is a function of r, so the derivative will be just this function valued at R. So you get this one. So if we know that any pair of random variables are circularly symmetrical, which is to say that the joint PDF is a function of GR, if you want to find the distribution of the distance, you could say that the PDF of the distance is the G of R, which is the joint PDF, times 2 pi R unit step function. So this is because R can never be negative. So the PDF of R of R is equal to 0 if R is negative. So this is why I have a unit step here. This unit step function is coming from here. And also for the CDF also you have a unit step. As example, you could assume that if the bivariate are jointly normal and circularly symmetrical, so in that case their variances should be equal to same, sigma 2, and the mean should be 0. And in that case, you see that this is equal to G of R, and G of R is equal to 1 over 2 pi sigma 2 and e to the power of minus R2 divided by 2 sigma 2. So from here, if I plug this one in this integral here, if I use this integral here, you could get this one, which is a Rayleigh distribution. If you calculate the derivative of these with respect to R, you can get PDF, which is the PDF of a Rayleigh distribution.